Hi everyone, welcome to the beginning of Math 344. We're going to start with a brief review of the idea of an infinite series and of power series. Power series are going to be the main tool that we use for the first third of the course, and then a modification of the idea of a power series will be what we use in the second part. So it's the most important idea in calculus that you were not made aware was the most important idea in calculus at the time when you used it. The material in this lecture corresponds to chapter 11.1 in the Goode and Annin book and is in the section called Power Series in my lecture notes. To remind you what an infinite series is, an infinite series is a sum, usually written in the form n equals 0 to infinity, of some terms that are usually denoted an. And the idea is that really when we write down an infinite series, we're not writing down some infinite sum. We think of it that way, but that's not really what it means mathematically. What we mean is the limit as capital N goes to infinity of the finite sums from n equals 0 to capital N of an. These things are called partial sums. Partial sums are the pieces that stretch out further and further and further to infinity. And the idea is that all of the rules of addition and multiplication work for partial sums because they're finite. It's only on taking the limit that we get something that looks like an infinite sum. And the idea with infinite sums is that it's a shorthand notation. It's annoying to have to write a limit as n goes to infinity every time I want to write down an infinite series, so instead I use the shorthand notation with an infinity inside of it. So we say that an infinite series converges if that limit exists and is finite. So if the limit as n goes to infinity of the partial sums exists and is finite, then we say the series converges. As an example of a convergent series, a really easy one would be something like 1 plus 1/2 plus 1/4 plus 1/8 and so on, which can be written as the sum from n equals 0 to infinity of 1/2 to the n. And that converges. You can calculate the partial sums. They'll turn out to be something like n minus 1 over n. You can compute a formula for this using the partial sums, and what you'll find out is when you take the limit, you end up here with the number 2. So there's a natural generalization of infinite series where instead of having a fixed sequence an inside the sum, we have some function that can change depending on the value of x that we plug into it. And that's what we mean by a power series. So a power series is a very special form. The terms in the sequence are monomials, where we have constants times something like x to the n. So a power series, and when I'm going to use the word formally here, when a mathematician uses the word formally, what they mean is I'm not telling you that this object means anything other than it's a pile of symbols. So formally what a power series is something of the form the sum from n equals 0 to infinity of an x minus x naught to the n. Now all of these pieces have names. This an here, this is a coefficient. And it doesn't move. Those are constant. X naught is called the center of the power series. And if you wrote this out, what you would end up with is something that looked an awful lot like a giant polynomial. And what we really like to have happen is that it acts like a giant polynomial. So what do I mean by it looks like a giant polynomial? If you took this formal object and you wrote it out, you would get a naught plus a1 times x minus x naught plus a2 times x minus x naught squared plus a3 x minus x naught to the third, and so on. And the idea here is that if you actually put in x is equal to x naught, then all of this collapses and all that's left over is the term a naught. Okay. Now I want you to notice I haven't used function notation yet because this doesn't yet represent a function. We have to say a little bit more because the coefficients that I stick onto this giant polynomial are going to dictate whether or not it forms a function. So we're going to use the definition of infinite series convergence to talk about when a power series converges. So let's just pick some value of x. for a fixed value of x, the sum from n equals 0 to infinity of an x minus x naught to the n. So the idea here is I've taken this x and I've actually put it right here. It's a fixed value now, so this is just some number, converges if, like before, the limit of the partial sums converges. The limit as k goes to infinity of the sum from n equals 0 to k of an x minus x naught to the n exists and is finite. So we've written down a rule now that applies to a single value of x. Now that's always going to hold for the value x is equal to x naught. So this series always will converge. It always converges at x is equal to x naught, because when you plug x naught in, this term becomes 0, and the only thing that survives is the a naught. So what I mean by that is the sum from n equals 0 to infinity of an times x naught minus x naught to the n is just the single number a naught. So of course that always converges. So what we've written down is the following. If we have the sum from n equals 0 to infinity of an x minus x naught to the n, it could be the case that this converges only at x is equal to x naught. It's possible that there's only a single point where I can plug something in here and this series makes sense. It could also be the case that I could plug in any x I wanted. Converges for all x in the real numbers. That's my fancy symbol for the real numbers. So any single x you choose, you plug in here and you get a series that makes sense. The third case is that there's something called a radius of convergence. There exists some r greater than 0 so that every x in the interval from x minus r to x plus r gives convergence. And this thing is called the interval of convergence. So the idea here is that this is the domain of numbers on which the power series makes sense. So graphically, there's three pictures that we can draw. We have convergence at a single point, or we could have convergence everywhere, minus infinity to infinity, or it could be the case that we have convergence on some interval that looks like this, where this distance is the radius r, and I have x naught plus r up here, and x naught minus r down here. And all the numbers in between, the series makes sense, and outside, it doesn't make sense. So converges in the interior and diverges on the outside. Okay, so the terms that we've seen so far are the interval of convergence, where we know that we've got convergence on the inside and divergence on the outside. This r distance right here was called the radius of convergence. And the way that we find the radius of convergence, or the interval of convergence for a given series, is we use the ratio test from calculus. So remember what the ratio test says is that the sum of an converges if the limit as n goes to infinity of the absolute value of an plus 1 over an is a finite number. So if this limit exists and is finite, then it turns out that the series converges. So we can take this idea and we can actually make it into a power series version, the way that it shows up in the book, in the following modification. The modification of the ratio test that we use for power series looks like this. For the series n equals 0 to infinity of an x minus x naught to the n, we compute the following limit. The limit as n goes to infinity of an plus 1 over an. And notice here that I've left the x's out of the picture. right? We're just using the ratio test on the coefficients, not on the x's themselves. You compute this limit, which is L. So there's three cases that we can consider here. If L is equal to 0, well, that means the coefficients get small really quickly. And what that means is that the radius of convergence R is equal to 1 over L, which is infinity. If L is equal to infinity, well, that means that the coefficients, as the series goes on and on and on, don't get small fast at all. And that's going to mean that the radius of convergence, which is 1 over L, is 0. So if you do the ratio test on a power series and you get a limit of infinity, then what that means is the power series only converges when you make all the terms equal to nothing. The last case is that if L is strictly between 0 and infinity, then the radius of convergence is just 1 over L. As an example, we could have a power series that looked like n squared over 3 to the n x to the n. This is a power series because it has a coefficient. That's the a to the n right there. A to the n, x to the n. I can use the ratio test on this to compute the limit as n goes to infinity of an plus 1 over an. If you write that down and then take the reciprocal of the denominator and multiply, what you'll end up with is n plus 1 squared over 3n plus 1 times 3 to the n over n squared, the limit as n goes to infinity. Computing the algebra on that question gets you the limit as n goes to infinity. I'm going to drop the absolute values because everything inside is positive, so there's no reason to have them there. The 3 to the n on the top and the 3 to the n plus 1 on the bottom cancel, and we end up with 1/3 times n plus 1 squared over n squared. And then using L'Hopital's rule or your knowledge of ratios of polynomials, it's pretty easy to see that the limit of this part is 1. And so the limit of the whole thing is 1/3. That's the quantity L. And what that means is that the power series has a radius of convergence 1 over 1/3, which is 3. And we can make that concrete and say what the interval of convergence by saying that the sum from n equals 0 to infinity of n squared over 3 to the n x to the n converges on the interval from -3 to 3. So for all those values, from -3 to 3, for those values, that's where this power series makes sense to think about as an object that has a meaning. Where power series are convergent, that is, on their interval of convergence, they converge for every x inside the interval of convergence. And that means that on the interval of convergence, it makes sense to define a function out of a power series. So where a power series converges, it defines a function. So if I know that the sum from n equals 0 to infinity of an x to the n converges on minus r1 to r1, then I can define a function by f of x is equal to the sum from n equals 0 to infinity of an x to the n. It makes sense in that case, since everywhere on this interval right here, I can put x into the power series, just make that a function. So f is a function that is defined on this domain, but not outside of it, just on this domain, by taking the x value and plugging it into the power series. And I know that's a sensible thing because if I do that, then I get a number out the other side. So f is a well-defined function. And likewise, I'm going to define, say, a function g of x to be equal to the sum from n equals 0 to infinity of bn x to the n. And let's say that this is a thing that's sensical on some different interval of convergence, minus r2 to r2. The beauty of power series is that once we know they converge, they act exactly like giant polynomials. So I can do algebra with them. I can add them, I can subtract them, I can multiply them, I can even divide them. Power series that are convergent are like enormous polynomials. It's a slight abuse to think of them this way, but it's useful to think of a power series that converges as a polynomial with an infinite number of terms in it. So let's suppose that we have f of x defined like we had on the previous page, a n x to the n. And we have g of x defined like we had on the previous page. So the sum from n equals 0 to infinity of bn x to the n. And we can define all of the operations on their joint interval of convergence as follows. First, I have to pick the smaller of R1 and R2 because I want both series to converge. So if we let R be equal to the minimum of R1 and R2, then both of the series will be defined on the interval from minus R to R. So if f has a larger interval of convergence and g's is smaller, then just look at g's interval of convergence, and then I can happily combine f with it. So what comes out the other side of this is the following. I can define addition exactly the way I do with polynomials. F of x plus g of x is equal to the sum of the coefficients times x to the n. The idea here is we're thinking about taking these things, sorting like terms, and then pulling the x's out. There's no justification for that because these aren't polynomials, but because they both converge, I'm allowed to treat them like they are polynomials. I can define multiplication the same way. So here's a scalar multiplication. I could write down c times f of x, and that's going to be equal to the sum from n equals 0 to infinity of c a n x to the n, which you can think about as sort of an infinite version of distribution. I can also define multiplication of series, which is more complicated because you can think if you have an infinite polynomial times another infinite polynomial, there's a lot of distribution going on. It's like a mega foiling, okay? But this is useful to know exists. It's not so hard to write down a formula for how to compute it. You can think about this as being something like a0 plus a1x plus ... times another gigantic polynomial, b0 plus b1x plus ... And the way that we write the series down that represents this is the sum from n equals 0 to infinity of cn x to the n, where there's a formula for the cn's. So the coefficients of the product series, the cn's, are just gotten by basically what you do is you take the polynomials and you multiply them out and collect like terms, and what you'll see is you're going to get patterns like a0 times b3, a1 times b2, a2 times b1, a3 times b0. And that's all that this formula right here actually represents, is that combination of terms. Now, there is a power series with which you are already supposed to be deeply familiar with, which is called the Taylor series. And the beauty of Taylor series is that it gives you a way of taking a function and writing down its power series. What we've done up to this point was take a power series and show how it defines a function. But if we have a function, it would be nice to know if it has an infinite series, and if so, what the interval of convergence for that is. So the Taylor series for a function centered at a point x is equal to a has this form. F of x is equal to the sum from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times x minus a to the n. And this is a power series. It's a special type of power series. And the reason that it's special is because we have a method for computing it. Now, the reason that the Taylor series works geometrically is that what you've done here by constructing this formula is you've made a power series that has the property that the derivatives all match with the function at the point a. So what I mean is that if I looked at x is equal to a, that this thing turns into f of a. And also if you took its derivative, it matches at f prime of a. And if you took two derivatives, it matches at f prime prime of a, and so on. So the Taylor series is the unique power series that has the property that its derivatives match the function. Since I've made the claim about derivatives, I should probably give you an idea of how you take the derivative of a power series so that you can see that I'm not just saying, oh, the derivatives match because I say so. If you have a function defined as a power series, so you have f of x is equal to the sum from n equals 0 to infinity of a n x to the n, and you take its derivative. Well, the power rule says that if you had a to the n x to the n, that you would pull the n down and you would reduce the power by 1. An is a constant, so it gets left alone. The fact that power series that are convergent act like giant polynomials means that I can use that rule by putting the derivative inside. And so the derivative here is n a to the n x to the n minus 1. Secretly, what I've done in the background here is I've used some math that you won't see justified unless you're a math major and you go into graduate school, probably, to say that the derivative of the sum of the power series is equal to the sum of the derivative. So like many things in this class, that's a statement that can be justified. It works because power series are convergent on an interval of convergence. So once you have that, then you can push the derivative inside and take it term by term, and that's where the formula comes from. If you take a second derivative, you end up with the formula, well, now you're going to take the n minus 1 that's up in the power and you're going to drop it down. You're going to reduce the power to n minus 2. But the stuff that was already there is still there. N times n minus 1, a n x to the n minus 2. And because this power series, if you put in 0 here, so if you took this 0 here and you plugged it in, you get 0 for the first term. So it's conventional to write this as the sum from n equals 1 to infinity of n a n x to the n minus 1, because why start with a series with a 0? Same thing here. If you took this 0 and you put it in, that whole thing turns into 0. If you increase the index by 1, you put in a 1, well, this turns into a 0, and so the whole thing is a 0. So you could also equally well just start the series at n equals 2. When a Taylor series exists, and it exists with a positive radius of convergence, we have the nicest possible kind of function in math. It has an infinite number of derivatives, and those exist on some positive radius interval. That sort of function is a very, very smooth function if all the derivatives exist to every order. That means no matter how many times you differentiate it, you're never going to find a discontinuity. No corners, no jumps, no nothing. Those functions are so nice they have their own name. So we say if f has a Taylor series on some interval of convergence with a positive radius of convergence, then f is analytic on the interval of convergence. And that means that f really is the nicest possible function. To give you an idea of some functions that we should just have the power series memorized for, the Taylor series memorized for, we have the basic fundamental functions of calculus. So you're supposed to know, for example, that e to the x has the series 1 plus x squared over 2 plus x to the third over 3 factorial, and so on. N is equal to 0 to infinity of x to the n over n factorial. And this converges everywhere. Next, we have that cosine of x is equal to 1 minus x squared over 2 plus x to the fourth over 4 factorial, and so on. In closed form, that has formula, the sum from n equals 0 to infinity of minus 1 to the n over 2n factorial x to the 2n, and that converges everywhere. And the related sine of x is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, and so on. And that has formula, the sum from n equals 0 to infinity of minus 1 to the n over 2n plus 1 factorial x to the 2n plus 1. And that also converges everywhere. So those are the three basic ones. I mean, there's more you could know, 1 over 1 minus x, natural log x. These are good power series to have in mind. The basic ones that we're going to be using over and over again here are going to be these. There's some subtleties when we're talking about some of the most basic functions that we're interested in working with. So one of the core classes of functions in analysis broadly and in science is the rational functions. So a rational function, f of x, is a ratio, p of x over q of x, where P and Q are polynomials. So for example, I might write down f of x is equal to 1 over 1 minus x squared. Or likewise, I could write down g of x is equal to 1 over 1 plus x squared. And I might think to myself, okay, if I wrote power series down for these functions, because every rational function has a power series as long as I stay away from the asymptotes, where is the power series for these things going to converge? The basis for computing the power series for these is the power series for 1 over 1 minus x, which is 1 plus x squared plus x to the third, and so on. It's the geometric series form. And by plugging different things in for x, I can very easily compute power series for these guys. So this has a power series that looks like the sum from n equals 0 to infinity of x to the 2n, because I just plug in x squared for x, and that gives me x to the 2n. This series converges for values between -1 and 1. It's obvious why that should be the case, because there's actually an asymptote at x is equal to 1. So if I start a power series at 0 and I reach out, it's going to be defined and defined and defined until I get to 1, and then there's an asymptote right here. So the function has to stop. It can't possibly have infinite derivatives at an asymptote, so it stops. And that means the radius of convergence is 1, and that means I can go back the other direction and also have -1. Okay? So if I find asymptotes in a rational function, that tells me where I can stop my interval of convergence. So obviously here, I have an asymptote at 1, and also at -1. And so it should seem pretty straightforward that the interval of convergence here is still -1 to 1. But what about this one? This thing has a power series that looks an awful lot like the power series for this guy, because you can rewrite it as 1 over 1 minus x squared. And that means you could plug the negative x squared into this formula, and you would get the sum from n equals 0 to infinity of minus x squared to the n, which you could rewrite as a power series if you wanted to, as -1 to the n x to the 2n. It's a good power series, has the right form. So the question is, this function had no asymptotes. Does it converge everywhere? And the answer is no. If you do a ratio test on this one, what you're going to discover is that the interval of convergence is still -1 to 1. So why? There were no asymptotes here. Why? This function is really smooth. If you did a graph of 1 over 1 plus x squared, you get a function that starts like this and does this bell curve shape out to infinity. Why does it only converge from -1 to 1? The answer is that this sort of mathematics is actually deeply bound up with the complex numbers, and that complex roots of polynomials end up dictating where power series converge. So it turns out to be the case that 1 over 1 plus x squared has asymptotes at x is equal to I and x is equal to -I. We're going to be going into more detail about how the complex numbers work when we get to the Fourier analysis section of the course. But for now, we know that it has to be I and -I because 1 plus x squared is equal to 0 happens whenever x squared is -1, which happens whenever x is plus or minus I. And if you think about the complex plane, what that means is that you have these numbers where you really have this disk of convergence. I can't go past the asymptotes in any direction, no matter how far, which direction I head. I have to stay inside of a disk that, centered at 0, can only go to where the first asymptote is in the complex plane. So actually, the reason that we even use the term radius here is because secretly what's going on in the background is in the complex numbers, there's this circle where the function converges. So because I have these complex roots, I still get the case that 1 over 1 plus x squared converges on -1 to 1. So it would be good to brush up a little bit on your complex numbers. I am going to use I instead of J because I'm a mathematician, not an engineer, and we're not going to be dealing with current in here. So you just get to deal with I as the complex unit. The last example for this section is to compute the radius of convergence of a rational function. Suppose you had the function f of x is equal to x plus 1 over x plus 2 times x squared plus 2. And I want to know the interval of convergence for its power series. Well, I don't know what the power series is, although I could determine it if I did polynomial long division. I still need to know where this formula makes sense as an analytic function. If I wrote the power series down, where would it make sense? So what I'm going to do is I'm going to try to find all of the zeros of the function that are in the denominator. That is, I'm going to find the asymptotes, even the complex asymptotes. Well, x plus 2 is equal to 0 when x is equal to negative 2. X squared plus 2 is equal to 0 whenever x is equal to plus or minus I root 2. If I think about where those would be on a disk in the complex plane, I have 1, 0 out here at negative 2, and then I root 2 is right here, and minus I root 2 is right here. And the radius from 0 in this direction is 2, and the radius this way is root 2. The largest disk that I can draw that doesn't contain any of these bad places in the function has radius root 2. And so the interval of convergence for this function will be minus root 2 to root 2. So that's supposed to be a review of how power series work, what a Taylor series is, how you manipulate a power series, their relationships with polynomials. So what did we cover? We talked about power series. We talked about convergence. We talked about the ratio test. We talked about Taylor series. We talked about rational functions. And we talked about derivatives of power series. I'll mention that power series can be integrated as well, but we're not going to be using integration of power series in this course. It's still good to know that if you can differentiate a power series, you can integrate it. So you can do calculus on it. If you want an exercise to amuse yourself with that, write down the power series for e to the x squared, and then take its integral. And you'll have solved one of the more famous unsolvable integrals from Calculus 1, Calculus 2. Okay, so this is an overview of what we did. This was chapter 11.1 in Goode and Annin. And next time, we're going to move on to talking about how to use power series to solve differential equations. All right, see you next time.